Okay. So yesterday we finished with a discussion of how we choose the method for the microbial control, right? There are plenty of consideration points. We have discussed some clinical examples, and we're going to focus more and more on why in certain situations you pick one and in certain situations you pick another. So what these microbial control methods can target. So if you think about this, there are few things that maintain the integrity of the microbial cell. One is cell wall, right? You can destroy cell wall, and then bacterial cells, especially cells with the wall, they will lyse, most likely. Okay? You can target the membrane, and you can target whatever is inside. Well, there are plenty of things inside, obviously. And those things inside, it's either protein, all kinds of proteins, because as we discussed, life is the form of existence of protein bodies, right? Things are made of protein. Or it can be nucleic acid, because nucleic acid carries the message in the cell and it contains the genetic information. Does that make sense? So heat and various oxidants target the cell wall, they physically destroy it. Okay, and cell lysis is the result. Cell membrane is targeted mostly by detergents, and we will discuss the physical mechanism behind it. And function of proteins and nucleic acid is targeted by a variety of different chemical and physical approaches, starting from heat and irradiation and finishing with various chemicals like alcohols and alkylating agents, phenols. Those are just examples. So you have to understand that this list of agents, it's not a complete list. Practically every chemical can, to some extent, denature either proteins or nucleic acids. Does that make sense? Now let's take a glance on physical methods of control. Before we talk in details about each one of them, what are three major physical approaches to microbial control? It's a temperature, it is radiation, and it's mechanical removal of microbes from whatever substance we're treating. Does that make sense? Let's talk about temperature first. What you can, okay, let's put it this way. You have something, you have a solution. In terms of temperature, what you can do with a solution? You can increase the temperature or you can freeze it, right? So you can make it hotter, make it colder. Let's figure out how each one of those approaches work, okay? Generally speaking, increased temperatures are bactericidal. When you increase the temperature, remember we talked about the protein denaturation, right? When you cook eggs, increased temperature, what does it do to the proteins? It denatures them. Exactly, denatures them. So that's why they bactericidal. Decreased temperatures are bacteriostatic. Think about the refrigerator that you have at the house. You put milk, I don't know, meat, whatever you put in the refrigerator, you slow down the microbial growth. They usually don't go anywhere, okay, but you just slow down that growth. Now, in terms of the heat, there are two types of heat, moist and dry. Moist heat is more effective than dry heat at the same temperature for the same microbe. That is important, for the same microbe. We always have to have only one variable when we compare two things. Does that make sense? Same microbe, same temperature, moist heat will be more effective. What does that mean, more effective? I'm going to give you a hint. Go back. I'm not going to go back. You go back one slide and tell me which parameter for the moist heat at the same temperature for the same microbe will be smaller than for the dry heat. Which parameter it is? Sorry, two slides back. The points of consideration. Yes, the points of consideration. Which parameter is going to be smaller for moist heat than for dry heat? It's like written in bold there, I think. No? Two slides back. Huh? The D value, exactly, the decimal reduction time. Moist heat, since it's more effective, it takes less time to decrease number of microbes. Does that make sense? The D value for moist heat is going to be smaller than for dry heat, given everything else is the same. Okay? Questions? Erin? Yeah, it takes less time. So for moist heat, it takes less time to reduce the number of microbes than for dry heat. So what about resistance? Of course, endospores are the most resistant. Then you go to bacteria, fungi, viruses. Okay, endospores are ridiculously resistant. Now, two parameters that are often applied to the heat treatments, heat inactivation. Thermal death time. It's the shortest time that requires to kill all microbes at the given temperature. Okay? Thermal death point is the lowest temperature that you have to use to kill all the microbes in 10 minutes. That makes sense. If you would look at this table over here, that's a comparison of moist and dry heat. Okay? So let's see. Thermal death time at 121 degrees Celsius. Are you familiar with Celsius, or I need to make it Fahrenheit? You're good with Celsius. Okay, so it's more than boiling. Okay? 121 Celsius. Thermal death time for moist heat is 15 minutes. For dry heat, 600. 40 times more. So it shows you the difference in effect. Can you see that? Okay. For instance, thermal death point for moist heat is 125. You see, 10 minutes. Time to sterilize. Does that make sense? Okay. So you can see that dry heat is much less efficient. What about, we're gonna go over different types of thermal treatments, okay? But freezing, first of all, freezing. Does it kill microbes? Does not completely. Depending on the microbe, for instance, sorry, if you take virus, we will start freeze and thaw the viral sample. Every freeze-thaw cycle will reduce the number of virus particles in the sample from 5 to 10 times. But if you have 100 million particles per milliliter, it'll take a while to eliminate all the virus. Does that make sense? Bacteria. Remember liquid medium that you worked with before, right? Liquid medium, the liquid culture of bacteria. So what will happen to this culture if I'll freeze it and then thaw it? Will there still be live bacteria? Yes. Think about this. You buy meat. You freeze it. You thaw it. If you thaw it and leave it in the container, it's still gonna rot, right? You don't kill all the bacteria in the meat when you freeze it. Does that make sense? Probably will reduce the load. Same goes for liquid culture. You will reduce the load. Bacteria will die. A lot of them will die because of the freezing. By the way, what kills cells when you freeze them? Yeah, you freeze the water and crystals, ice crystals. They not only, what about density of ice compared to density of water? The ice is not. Ice has less density, which means when water freezes, it expands. Think about this. If you put the bottle filled with water into the freezer, your lid will come off because water will expand, or bottle will just explode. Does that make sense? So cells essentially explode. Well, many of them explode when they get frozen. Okay? That really, there are animals that you can freeze and then thaw, but they have components, biochemical, they have molecules in the cytoplasm that prevent cytoplasm from freezing. Okay? Ice crystals do not form. So freezing is not really a good method to destroy the microbes. It's a good method to kind of delay the multiplication, the microbial effects. Now what about heat? So, moist. Everything up here is the moist heat. Pressurized steam. Autoclave. I'm going to point over there. There's an autoclave behind that wall. If you have a pressure cooker at home, it's a miniature example of an autoclave, pretty much. Okay? Autoclave has increased temperature, increased pressure. Usually it's 15 psi, which is approximately 1.5 atmospheric pressure, and 121 Celsius altogether. It is a sterilizing method of microbial control, no doubt. Of course, the time it takes to sterilize things is different for different things. If you want to sterilize a beaker, or you want to sterilize a mouse, which one will take longer, a mouse or a beaker? Mouse. Why? Exactly. Heat has to go all the way inside. Generally, the regimen for like glassware and surgical instruments, 15 or 20 minutes in autoclave in these conditions. For mice, we autoclaved mice, 45 minutes. And they stink afterwards. Steam. Not pressurized steam, regular steam. This method is also called Tyndallization. It was developed by John Tyndall in, I want to say end of 19th century, but I'm not really sure about time frame. Anyway, so here's how it works. Remember we talked about endospores, right? When do they germinate? What is the signal for endospore germination? When they start to produce vegetative cell, what should happen in the environment? Which chemical should appear in the environment? Critical chemical. Very simple chemical. Water. Because they formed mostly when cells become desiccated, right? And then when water appears back, endospores start to germinate. So what Tyndall did, he used a very elegant, although quite elaborate method. You have, scissors, and you expose them to steam. Steam kills vegetative microbes. Does that make sense? Like the normal replicating bacteria. Does regular steam kill endospores? It does not. No, it doesn't. Temperature's too low. And then you leave this scissors after they were exposed to steam in that sterile chamber. You don't open anything, you just keep them there. What happens to the steam as the chamber cools down? It condenses and produces what? What happens to the endospores? They germinate, they become vegetative cell, and then you hit them with the steam another time. So those vegetative cells are killed, and then you let another cycle to go through. You let this chamber to cool down again. More endospores that are left germinate. Generally, it is considered that 3 cycles is sufficient to kill all endospores. Essentially, you don't kill endospores, you force them to germinate and then kill vegetative cells. Does that make sense? It's like whack-a-mole. You wait for the bacteria to appear from endospore and then hit it with the steam. Make sense? The problem with that method, how can you guarantee that after 3 cycles you actually killed all endospores? But before autoclaves it was used quite a lot, and convenience of that method, it can be used in poor areas, okay? Areas where you don't have the access to autoclave. It's very simple technologically. Pasteurization, treatment with a high temperature for a short period of time. Flash, 15 seconds for 72 degrees Celsius. Batch method, 30 minutes for 63, 66. Now, this method is not sterilizing, it's disinfecting. But what is important? It kills most microbes, well, practically all important microbes that can cause gastrointestinal infections and food poisoning. Does that make sense? Another importance of pasteurization is that it saves the taste and the smell of the food to a large extent. Let's be honest, it does. And in fact, Louis Pasteur became a French national hero, not for rabies vaccine, not for the germ theory of disease. What did he invent? For which industry in France? Wine. Who cares about milk? Who drinks milk in France? Come on. It's not Wisconsin. Wine. They had a problem. Wine went bad in sometimes few days. And he developed method of wine pasteurization and saved. He often is claimed as a saver in French wine industry. Boiling, disinfecting, not sterilizing method, okay? So when you boil, I don't know, pacifier for your first kid, you're not actually sterilizing, just disinfecting. There's still probably going to be some endospores on it. Okay. So this is moist heat. What you have to know about the methods, whether they are disinfecting or they are sterilizing. So do they kill endospores? Do they not kill endospores? And I'll mention a few things about pasteurization just a bit later. Okay. Now, incineration and desiccation. Incineration is definitely sterilizing. You burn something, everything's dead. You physically, there's no chance something can survive incineration. The device is burners, and you have these fancy things. This is called infrared incinerator. I'm actually going to plug in mine, just for kicks. It's convenient because it doesn't produce the open flame. You can take out yours if you want. So the good thing, no open flames. The bad thing, takes a while for it to heat up, but it's really convenient to work with. So essentially, they have a wire loop. Yeah. So once it is hot and you can see it's red, bright red inside, you stick the wire loop in, hold it there for like 5-6 seconds, and it's sterile. It's pretty cool. Desiccation. We talked about desiccation as the control method. Dries out. Microbes cannot survive without water. So, especially in the food industry, desiccation is extremely important. We knew desiccation for years, jerky, dried fruits, so on and so forth. Prevents food from rotting. Can you use dry oven to sterilize things like surgical instruments or glassware? The answer is yes, but it takes a lot of time. So for endospore killing, you got 180, 2 to 4 hours. Usually in the labs, if you want to sterilize glassware, the temperature is set at 270 degrees Celsius, which is not really feasible at home in an oven. And it is run, often people just put the glassware overnight. It's just easier. Okay, I've heard a story when a person accidentally put the plastic box with a Drosophila, the fruit flies, instead of incubator, into 170 degrees dry oven. Turned on the oven and left. When she came in the morning, of course, there were no Drosophila, but what's funnier, there were no box. It evaporated overnight. They had a ventilation in that oven, so it was pretty neat. So this is how it looks like. This is some goddamn fancy incubator, autoclave, believe me. What we used to operate, old style door, like in a nuclear war bunker, and the wheel on front, and you have to, turn it one or another side. That's your infrared incinerator, desiccation essentially, and this is pasteurization. In fact, there are two. There's one more type of pasteurization, ultra high temperature, when milk is heated for 2 seconds to more than 100 degrees Celsius. So it's very short time, very high temperature, and it allows this milk to be stored at the room temperature. So this one, okay, the flash method, pasteurized milk still has to be kept at 4 degrees. Okay. Now, what is so important about pasteurization that I wanted to mention? Look what it kills. It can kill Campylobacter jejuni. It's a gram-negative microbe that is a leading cause of diarrheal disease in the United States. Coxiella burnetii, well, it's kind of fun. It's not very much important digestive pathogen. Listeria monocytogenes. Have you heard about listeriosis? So it's a disease that's associated with a lot of food products in the United States, from poultry to milk to cantaloupes. Okay, E. coli 0157H7, hemolytic uremic syndrome. Anyone heard? It is also called enterohemorrhagic E. coli, EHEC. Causes extremely severe diarrhea with dysentery, blood in the stool, and may cause hemolysis in patients. Hemolytic uremic syndrome means hemolytic, hemolysis, uremic, urine, increased concentration of urine in the blood. Okay? Does that make sense? So it's kidney failure, pretty much. M. tuberculosis, Mycobacterium paratuberculosis. That's actually an enteric microbe. Salmonella, doesn't need any introduction, I suppose. And Yersinia enterocolitica is often called orphan infection. It is when somebody is present with gastrointestinal symptoms, doctors rarely check for Yersinia enterocolitica, and rightfully so, because it's not very frequent. But, if they cannot find what is causing the disease, maybe it is. So it is actually a causative agent of diarrheal disease, not just very frequent. So all these microbes, as you can see, a lot of them are important causative agents of diarrheal disease. And I want you to understand that pasteurization can effectively get rid of them. Does that make sense? Radiation, two types, ionizing and non-ionizing. Ionizing radiation can cause double-strand breaks, right? So these DNA breaks make microbes unable to replicate, and they die, essentially. There are three types of ionizing radiation: cathode rays, X-rays, and gamma rays. Gamma rays have the highest penetration ability. Cathode ray has the lowest penetration ability. Honestly, for sterilization purposes, the most widely used ionizing radiation method is gamma rays. There are radioactive nuclear isotopes that can by themselves produce gamma rays. So it's essentially so-called gamma ray cannon. The isotope, I think it's cobalt-50, I'm not sure about, I think it's cobalt, one of the cobalt isotopes, can be placed in the chamber, and those gamma rays can be focused on the certain space. And you can run the conveyor belt through that space and sterilize things that cannot withstand heat, like sterile plastic goods for operating rooms, for instance, like syringes, catheters, tubing. Does that make sense? Another thing, food. I mentioned before, and my spouse works at Case, and they study inflammatory bowel syndrome. And one of the tools that they use is so-called germ-free mice. Mice that do not have any microbes in their intestines. That is pretty neat. So they have, for instance, the feces of these mice, they do not smell. Mice do not smell. You walk into the mouse colony, there is no smell of rodents, because they have no bugs in the intestines. So, and of course, you cannot give them regular rodent chow. You have to sterilize it first. And the food that comes, it is irradiated, gamma irradiated. There are people who are immunocompromised. You may have heard about boy in a bubble, people that lack immune system almost completely. Their food has to be irradiated. So that's what you use gamma radiation for. Obviously, I mean, you can take a hamburger, stick it in an autoclave. What you get out is still food. It's still technically digestible. I don't think it's going to be attractive anymore. You know, try to boil the hamburger. Okay, so that's why gamma rays are used for food irradiation. Things like fruits are often, obviously they're not sterilized, but the bacterial load on their surface can be decreased, so the storage time increases. Does that make sense? And it's convenient, you don't have to load batches. You can just irradiate on the conveyor belt. Okay, non-ionizing, it's a UV light. UV light leads to the formation of thymine dimers, okay? So it's non-ionizing. It has lower energy, doesn't kill endospores, kills vegetative bacteria, kills fungal cells, viruses, protozoa. So it's not sterilizing, it is rather disinfecting. Can be used for operating rooms in hospitals. Now, the advantage of this method Have you seen the large UV lamps? Well, there are UV lamps right there. Now, can you scale it up? Sure enough. You can scale it up, make it standing, put 5, 6 of them in a circle, stick it into the room, plug it in, turn it on, and just leave the room. And you can leave it in the room for an hour or two, and it will effectively disinfect all the surfaces in the room just by UV light. Does that make sense? You can see on this picture the UV light that is used in the hoods, biological safety hoods. After you finished working, you worked with, say, bacteria or viruses, okay? Turn on UV light, you close the sash. In the modern hoods, you have to close the sash in order for UV light to work, so you don't burn yourself. And then you go. And you can leave it overnight, and overnight everything gets killed by the UV light inside of that hood. You come next morning, you open it up, turn on the blower, and let it run for 5 minutes. Reason for that? UV light leads to the formation of ozone. Okay? And ozone is extremely toxic to humans. Really, it's very toxic. So this ozone accumulation, you just blow off the ozone from under the hood, and then you can start working. Okay, but it's pretty effective. We kept the hoods pretty clean and nothing grew. Yes. Much stronger. I cannot give you the energy per square centimeter, but think about this. When you go outside and you take a sun bath, it's all kinds of electromagnetic spectrum. When you use this, it's only UV light, nothing else. So in terms of energy density, how much energy goes per square centimeter is going to be higher. I like that story. I was a part of forum molecular biologists, like students and postdocs. And one guy said that he had an old version of that hood, which did not turn UV light off when you lifted the sash. So he went in there, lifted the sash, and started to work. It took him 15-20 minutes. He was like this. He pulls out, and he has a great brown tan all over his... So 20 minutes, from white to brown. Okay? It's really intense. Really intense. Another use of this, water treatment. Again, it's a combined effect, UV light and ozone. Okay? And again, it's convenient because you can use these setups. First of all, which one is safer for the personnel that works with it? UV light or gamma rays? UV, yes. It's not 100% safe, but it's safer. It's not penetrating radiation, right? So you can get sunburn. Okay. People can deal with that. So you can install it in the large industrial settings, like water treatment plants. Okay, it's convenient. You can do it, and you don't have to take a lot of precautions. And let me tell you something. Dealing with radioactive material, in terms of regulatory restrictions, it's a pain in the ass. Because you have to log every microgram of it. God forbid you lose something. UV light is easy. There's no radioactive material involved. That makes sense? Filtration. I don't even know. Do you need explanation how it works? You have a filter with the pores. It doesn't let bacteria through. That's it. So actually there are 4 different kinds of filters that are commonly used for water filtration. This photograph over here, in the center that I just circled blue and now red, it shows you actual setup. What I like about those illustrations, they show you what you're going to see in the lab, clinical or research lab. So this is probably 0.22 micrometer filter. So 0.22 retains all bacteria. It doesn't retain fragments of bacterial cell wall though, which means things like lipopolysaccharide and the toxin fragment of the bacterial cell wall can still go through and called pyrogenicity. Okay, there is 0.45, which is not sterilizing. There's 0.1, which is not only sterilizing, it also makes solutions non-pyrogenic. What does pyrogenic mean? You're thinking in the right direction, but in relation to humans, pyrogenic. If the solution is pyrogenic, drug is pyrogenic, compound is pyrogenic, what it causes in humans? Fever. Yes. So non-pyrogenic do not cause fever. Does that make sense? Okay. You can see that filters can be like bench top, or you can put them on the syringe. Why you need this? Imagine that you prepared a one-time injection of, I don't know, antibody, something in the field conditions, and you're not sure about how sterile your preparation is. You can stick on the filter, run it through the filter, whatever comes out from this end is sterile. Okay? Now that's fluids. What about air? There's a filter that is called HEPA, high efficiency particulate air. You can find it in the hospitals, places like operating rooms or burn units. The movie that we watched yesterday, The Fragments, okay, BSL-4 units. In BSL-4, as I mentioned, as we figure it out, nobody cares about you when you work in there. Everybody cares about environment. So the multi-stage system of filters prevents the escape of any pathogens that you work with into the environment. Make sense? Okay. One thing that I wanted to mention in BSL was sort of a digression. So as you can imagine, when you handle water in BSL-3, well, based on my own experience, you handle water, you put something in a sink. You're not, you don't dump biohazard materials in the sink, but microbes can accidentally get in there. So you cannot run it into the regular sewage. Does that make sense? So this is what we had. We had a sink, and we had a bucket under the sink. I think it was about 11, 12 gallon bucket. And no faucets were movement activated, so don't touch anything. And once the bucket is, close to being filled up, you close it, you stick it into the autoclave. You run autoclave, you take the bucket out, dump on the other side, on the clean side, dump the autoclaved water, bring the bucket back in. It was an elaborate process. But anyway, and you must not forget to check the level every time you wash hands and so on. So one evening, as it turns out, 2 grad students were working there in the BSL-3 labs, and one checked the bucket, and it was about 3/4 full. Strictly speaking, there's still space, but only if you're an asshole. And it's like 4:30 p.m. in the evening. Come on. You close the bucket and you stick it in an autoclave. You don't have to wait till the end of a cycle. You can take it out next morning. It's not a problem. We have plenty of empty ones. But she decides, no, I'll just leave it at that. It's not full. and she goes home. Another student, she didn't check, to be honest, she didn't check the levels, but she thought, it's okay. And she was leaving too. She placed the bottle with disinfecting spray next to the faucet. I can't reach the faucet, but imagine this is the faucet. Okay. She placed it like this and went home. Well, I told you, it's movement activated. It's not just movement. They have a photo element. So if something stands in front of the photo element, the faucet considers it somebody's washing the hands, and it turns on the water. So she left, water got turned on after she left, and was running the entire night. In the bucket there was like 2 gallons of space. Next morning I come to work. I didn't have to go to BSL-3 that day. Come to work like 9 a.m. in the morning, it's fine, we have flexible schedule. I usually work like 9 till 6, 9 till 7. I come in and my colleague, she's really upset, and she says, don't say anything, just go upstairs right now. Just forget about it and just go over there. And I go there and everybody's so pissed upstairs, as you can imagine. Lucky we, BSL-3 unit is built not only in the way that air goes in, the floors in the BSL-3 are lower than the floors of the outside facilities. So in case of water leakage, the water doesn't start to leak out potential contaminated water. Turns out in the morning there was ankle high water. It didn't leak. It was ankle high. And we had to dress in a BSL-3 suits like the one I showed you yesterday, with the air pump and the hood and everything. And we spent about a day just cleaning the facility from water. It was still contaminated. So you go in, you do all the procedures, you go in, and you start to collect water, you know, with old style, with towels and everything, and you autoclave all those buckets with water. The entire day was just thrown away. And violation of the federal rules, how to handle the pathogens in a facility, is not a misdemeanor, it's a felony. So if you violate the rule, even inadvertently, you go to jail. So my then bosses actually left eventually, because they said they had to handle the entire facility themselves, all the regulatory stuff, and they said we're gonna move to another university. In University of Pittsburgh, they have BSL-3, but they have special team of people like safety engineers that handle all the regulatory things, like running, cleaning, autoclaving, and all that kind of stuff. So much easier. Anyway, before we move to chemicals, I'm not going to go over the table. It's a summary, okay? One thing that I want to specifically mention, we did not discuss lyophilization. I'm not going to ask, just want to tell you, lyophilization is freeze drying. You simultaneously dry something and cool it down. It's a preservation, not sterilizing technique, okay? Other than that, well, we discussed the role of salt, okay? Other than that, everything else we have discussed. So it's a summary for you. Does that make sense? Now, chemical methods. There are many chemicals that we use for cleaning. It's kind of a dumb statement, I know. But you go to the supermarket and you see Lysol, Pine Sol, Clorox, all that kind of stuff, you know, all over the place. And they're all various types of chemical disinfectants. When we go into the healthcare, there are other disinfectants. We talk about chemicals that are used for aseptic treatments, like rubbing alcohol or betadine, okay? Chemicals generally can be divided into the water-based, that's what we use at home, and tinctures or alcohol-based. You're probably not going to use tinctures to treat surfaces. They're too expensive. And often the reasons why alcohol is used as the solvent, because of the poor solubility of the active compound in water. You understand what I'm trying to say here? If you try to dissolve soap in water, it dissolves really well in water. If you try to dissolve iodine in water, good luck with that. It's one of the first labs that we did in inorganic chemistry in college. You take iodine crystals, you pour water on top, you have crystals, and you have lightly brown water. And that's it. And they just gonna seep there. They really poorly dissolved in water. We're gonna talk what this solution of iodine that is applied to the skin is. What do you want from chemical? Can you try not to look at the PowerPoint and tell me, what do you want from disinfectant chemical? What do you want from it? It disinfects, so it should be efficient. Do you want disinfection or sterilization is better? Of course, sterilization is better. It should be cleaning the hell out of the surface, right? What else? Not toxic or not irritant. Well, good luck. Okay, let's put it this way. Limited toxicity, obviously. If it kills microbes, it will probably kill you. What else? Huh? Acts quickly. It doesn't have to sit for 3 hours. What else? Cheap. That's very important because you use it in a huge amounts. No. Elaborate on that. So when you put it on surface, what? Exactly. It's not gonna damage whatever you treat, right? I can use sulfuric acid. It's really good sterilization chemical. It will kill all the microbes and humans alike. It will also probably dissolve the hell out of the surface that you use it for. Okay, but it's good. So yeah, not damaging surfaces, not corrosive, not something like that. What else? Stable. You don't want something that, you buy and in 3 days it loses all the power. That makes sense? When you clean, forget clinical settings. When you clean the kitchen, you clean the mess in the kitchen, what is there? What's on the counter? Microbes, huh? Food. Yeah. So organic compounds should not inactivate or minimally inactivated. Does that make sense? You see what I'm trying to say? So that's also really important. There are plenty of, it should smell well. I once prepared a really concentrated solution of pine sol. My wife came in the kitchen, just opened all the windows. She said she cannot tolerate this. Okay. There are chemicals, think about this. The mildew and mold remover, like the tile cleaner, it really is a great disinfectant, but you have to work in well-ventilated areas or not expose yourself for an extended period of time, right? Because it stinks and it's also toxic. So there are plenty of qualities, okay, that actually do not go together really well. We're going to discuss, we have a spectrum of different chemicals that are used in different settings, depending on what you try to achieve. So we have to consider the nature of microorganism. What you try to destroy. Do you try to destroy endospores, or you can just get away with killing vegetative cells of bacteria? What are you treating? Obviously, if you treat patient and you treat stainless steel, they have different levels of resistance, okay, to the chemicals. How contaminated it is, how long can you leave it on? And I will give an example, okay? And of course, we need to, taking all of this together, we need to match a purpose with what the germicide is, what the chemical is. This table gives you rather non-systemic view of different germicides. Well, one leader, obvious leader, is hydrogen peroxide. Okay, kills all kinds of things very quickly. Chlorine is pretty good against vegetative bacteria. Okay, different concentrations. Ethyl alcohol is rather slow, so you have to leave it on. It doesn't work that well with alcohol. Quaternary ammonia, rather slow. Ethylene oxide. We'll talk about ethylene oxide, how it works, and what it is, and why it is sterilizing. Now we're going to start with halogens. There are plenty of, well, plenty. There are 5 halogens. It's a 7th main group of periodic table. Fluorine, chlorine, bromine, iodine, and acetate. Acetate is not ever used for anything. It's radioactive material. Forget about it. Fluorine is extremely reactive. Extremely. When you mix fluorine and hydrogen together, for instance, they explode. Like, you don't even have to start anything. They just explode. Fluorine is extremely reactive gas, so it's not really possible to use it. It's probably going to be the perfect sterilisant because it would destroy everything, including the material you try to sterilize. Bromine, why we don't use bromine? Have you ever seen bromine at the room temperature? Chemical lab. Probably. I mean, it's very toxic. At the room temperature, it's liquid. It's very toxic, heavy liquid. It can cause chemical burns, can cause respiratory irritation because it produces vapors. So we end up with chlorine and iodine. Did you ever see elementary iodine? No? It's a lot of fun. Crystals. Huh? No, it's not iodine that will explode, but thank you for reminding. If you take iodine crystals, I didn't say that. I mean, it all goes for the record, but it wasn't me. It's not me who's talking. Take iodine crystals, take some concentrated ammonia solution, and pour ammonia solution over the crystals. Let them dry out. Make iodine azide, and it will explode if you touch it. It's a lot of fun. You can put it in somebody's seat. It's not going to like rip the butt off, but it's going to scare the shit out of the person. Works well against pets like squirrels and cats if you put it on top of the fence. They will stop crawling over the fence ever. Okay. So iodine is crystals. Chlorine is gas. Chlorine is much more active. You can see chlorine is stronger in strength than iodine in terms being an oxidizing agent. Now, chlorine as the gas is really inconvenient to handle. In fact, during World War I, it was used as the chemical warfare by Germans. I myself, first year of college, we had a lab. We were making chlorine. So how you test there's a chlorine in a tube? Technically you should do this, right? You hold the tube and you smell like this. Well, who does it? That's how you do it. I had a runny nose. I stopped having runny nose. I also didn't smell anything for 2 days. All microbes and mucosal cells alike died. So chlorine as the gaseous compound is inconvenient to handle, reactive, very toxic, and it's really hard to work with gas. So what we do, we dilute chlorine in the water and it produces bleach, okay? Hypochlorite, okay? Can also make chloramine. When chloramine is diluted in water, it will produce ammonia and chlorine radical. Okay, ammonia, great for cleaning as a detergent. Chlorine radical is very oxidative. Okay, so we use water, pretty much water solution of chlorine. That's why when you take bleach and you start to spray this mold and mildew remover, what you smell is the smell of chlorine gas that is being released from that solution. That makes sense. So it is toxic, and its main mechanism of action, which you should know, oxidation. It oxidizes cell wall and oxidizes proteins and so on and so forth. Okay. Now, can it sterilize? Yes, it can sterilize. With the extended exposure, it can kill endospores. The high concentrations, extended exposure chlorine can kill endospores. Does that make sense? Iodine. It's antiseptic. Okay. Mostly used for the skin treatments before surgeries, injections. You saw it all. You're treated. Now, why we call it betadine? Because iodine itself, as I mentioned, is not really well dissolved in water. So you have to add something else. Usually, there's water mixed with alcohol. There's also a polymeric substance called polyvinylprolidone. Don't write it down. You don't have to know that word. Okay? Which increases iodine solubility in that mixture. Increases its concentration in the mixture, making it far more efficient for antiseptic treatment. And it also oxidizes cells. Does that make sense? So halogens, they take home message, main mechanism is oxidation. Chlorine can be sterilizing. Iodine is used for disinfection and aseptic treatments. We good? We can move on. Any questions? Phenols and bisbiguanidines. Phenols, shown on this picture here. Technically speaking, phenol is only this molecule. It's an aromatic compound. It's chemically active, solid at the room temperature. If you take the phenol crystal between your fingers, you're going to get chemical burn, mild chemical burn. It's pretty toxic. First person to use it was Joseph Lister that we mentioned, the first unit. He made a water solution of phenol called carbolic acid and used it to spray on the wounds of the surgical patients. It was, from modern standpoint, pretty cruel treatment, but at least it prevented wound infections. And even in 20th century, carbolic acid was used to disinfect and sanitize hospital surfaces, wash floors, toilets and whatnot. Surgeons actually used carbolic acid to wash their hands, which of course didn't make their skin any better. It's quite chemically aggressive still. So phenols are not extensively used in medicine right now. We'll talk about some of the recent uses. For a long time, the parameter called phenol coefficient was used to assess the antimicrobial effectiveness of various chemicals. So phenol coefficient compared the chemical of interest with the phenol. Does that make sense? So if it was like 10 times more effective than phenol, then phenol coefficient would be 10. Okay. I want to mention a few words about these guys, the creosotes. Have you heard about the compound called creosote? It's an old style compound. It's produced, used to be made from mostly birch, like a tree. Okay, it's dark, oily fluid. Now I'm gonna stumble into the lack of English language knowledge. Railroad tracks, you have rails. They are connected by what? I don't know the word. Thank you, the ties, yes, the railroad ties. Most railroads that you can see around, the ties are made of cement, right? But some older ones, you can see the ties are made of wood. And this wood is very, very dark, almost black. It is black because it's heavily infused with creosote. Creosote has two main active compounds, O and P creosols. They have powerful antimicrobial properties that prevent wood from rotting. Does that make sense? Now, chlorophene and especially bisphenols. Bisphenols were used in the different plasticware, plates, bottles, to prevent bacterial growth and whatever is in the bottle. The only problem, turns out that they have certain endocrine toxicity. In rather small amounts, they screw up human hormonal levels. And bisphenols got banned with the current level of sterilization technology we find without bisphenols. So like this one, it says BPA free, so bisphenol A free. Okay, it's food safe. Another interesting compound right here, it's a phenol compound as well. It is called triclosan. If you take antibacterial soaps, different antibacterial cosmetic products, you're going to find triclosan in there. Okay, it is pretty safe for humans. And the belief was that using antibacterial soap will decrease the rates of the hospital-acquired infection and community-acquired infections, bacterial infections. It's a conceivable idea, right? It's reasonable. You use antibacterial something, you're going to decrease the level of transmission. So what happened? People started to use antibacterial soaps, and triclosan that was in the soap started to pour where? Wash your hands. Where does this all go? Down the drain. Gets into the sewage. From the sewage, it gets into water supply. Environment. Yes, it goes into the environment. The amount of triclosan that humans dumped in the environment was so significant that bacteria started to evolve and gain what? Resistance, yes. Practically all bacteria now are resistant to triclosan. To make things even worse, later tests showed that triclosan in the first place, at the concentrations that we used in the soap, in those concentrations it had very limited, if any, effectiveness against bacteria. Multiple studies showed that regular soap and antibacterial soap have practically no detectable difference in terms of how they reduce microbial load on your hands. This is pretty sad. And it's an official recommendation of I don't know which agency, CDC or FDA, one of them. They said they recommended not to use antibacterial soaps anymore because it only leads to the development of resistance, further development of resistance in bacteria, but doesn't provide any benefits. Chlorhexidine belongs to the group of chemicals known as bisbiguanidins. It's the base, organic base, complex. It leads to the disruption of the membranes and denaturation of proteins. So since it's a membrane disruption, it's not sporicidal, it doesn't kill spores, but it's pretty effective disinfectant. It's one of the best disinfectants for clinical use. It is safe, works in rather low concentrations, not very toxic to humans, non-toxic to skin. Do you know where it is used? Any examples? Huh? Yes, dental wash. Yes, exactly. Well, I say dental wash, I mean mouth. Yes, yes, mouthwash. Yes. Other genital places. OBGYN. Okay? It is very mild to mucosal membranes. Can be used in OBGYN settings, surgical settings, baths for patients in hospitals and people in the nursing homes. Chlorhexidine is very widely used, so let's wait when microbes will develop resistance to it. I didn't mention what are the modes of action for phenols. It's the same membrane disruption and protein denaturation. Okay? Does that make sense? Now, several chemicals, I kind of squeezed them in one slide here. Alcohols. We use two. We use ethanol and isopropanol. Rubbing alcohol is isopropanol. Hand sanitizer is ethanol. So these guys denature proteins and disrupt membranes. Why do we use isopropanol as for the rubbing alcohol? People just gonna drink it if it's gonna be ethanol. I'm dead serious. I'm absolutely serious. We had in the lab, we had a special name for ethanol. So nobody ever had the word ethanol on the bottle. I'm dead serious. So you call it like buffer C, something like that. Because it's usually very pure and you can make a pretty good drink out of it. I can vouch for that because I did that. We made drinks from the lab ethanol. It's pretty good, high quality. Much better than probably half of the vodka products in the liquor store. Isopropanol, if you drink it, it metabolizes to become acetone, so it's toxic. Shouldn't drink, and people know that they shouldn't. Drinking hand sanitizer is not a great idea. So, interesting feature of the both rubbing alcohol and hand sanitizer is that it's not extremely effective against viruses that do not have envelope. So, anyone remembers, what does the viral envelope consist of? That's capsid. Envelope is something, phospholipids, membrane, right? And these guys, ethanol and so the alcohols, they disrupt membranes. Since there's no membrane, they cannot disrupt it. Why I tell you this? Here's the story. Have you heard about norovirus? It was actually discovered 60 miles from here, Norwalk, Ohio. Yeah, it was isolated in Norwalk, Ohio, and there's a great story associated with it. So norovirus is the big problem in certain touristic environment. No? Yeah. It's not a flu, it's stomach virus, yes. But where? In which certain places where people spend their vacations, it just can ravage and make your vacation hell. A lot of people confined in a small space, isolated from dry land. Huh? Well, not for that long. Huh? What? Cruises, yes. It's often called a cruise ship disease. If there's a person on a cruise ship with that disease, all 2,500 people are going to have it at one point or another. I mean, it's fairly mild. It's called two-bucket disease. So you have diarrhea and vomiting for 24 to 48 hours. Still unpleasant, right? So cruise ships were really concerned, cruise companies were really concerned about this problem, and they wanted to deal with that. They actually implemented very rigorous cleaning protocols after the cruise, so at least the ship is clean before. And they also started to install hand sanitizers, which do not help against norovirus. They installed like thousands of them in all places in the ships, but they do not help. Honestly, they also installed, I've heard that they started to install automatic hand wash stations. So like, stick your hands, washes them, pull them out. The only problem, they didn't install automatic hand dry stations and no towels. So what people do, once they wash them, they do this and go in. It doesn't really help. Now, peroxides, different chemicals that contain in one or another form a chemical group like this. So peroxides, you have one at home, it's hydrogen peroxide. It's very good disinfectant. Generates reactive oxygen species, if you expose the surface to a higher concentration of peroxide for a longer enough time, it can be sterilizing. There are chemicals that are actually sporicidal. Spore clans is the combination of acid and peroxide, so-called peracetic acid. That makes sense? I can tell you, imagine it's a combination of acetic acid, like a vinegar, high concentrated vinegar, and hydrogen peroxide. You should operate this chemical wearing a respirator. So it's really aggressive, it's toxic, it's not really safe to work. It's used for sterilizing the surfaces, not at home. Another interesting device is using vaporized hydrogen peroxide. You can use it to sterilize things like stethoscopes, okay, in a small containers. Or, again, the same company, Steris and Matter, they produce special vaporizers. You can put it in the room. Remember I told you can sterilize the room? You can put this device, this generator, in the room, and it will produce vaporized hydrogen peroxide. And it can produce it for hours, filling up the room with hydrogen peroxide vapors. The only thing you have to have is you have to have ventilation, so it is sucked away, okay? And that essentially is sterilizing treatment for the rooms. It's used in the surgical suites, in BSL rooms, and so on and so forth. Does that make sense? So essentially, oxidation is the main mechanism by which hydrogen peroxide and other peroxides work. Oxidation leads to the destruction of cell wall and vast denaturation of proteins. Now, surfactants. We're going to talk about surfactants and take a little break. Surfactants. What does the word mean? Surface active compounds. Yes, surface tension. Yes, they really reduce the surface tension, and they essentially disrupt the membranes by inserting themselves inside. Surfactants can be cationic or anionic. Anionic surfactant is the soap. It has negative hydrophilic head and hydrophobic tail. Now the surface of bacteria is also negatively charged. So anionic surfactants do not effectively bind to the surface of bacteria. Does that make sense? Negative charge doesn't really attract to another negative charge. Does that make sense? On the contrary, cationic surfactants, like this benzalkonium, which has positively charged hydrophilic head and hydrophobic tail, these cationic surfactants, they hydrophilic heads can bind to the surface of the bacterial membrane and introduce themselves into the membrane. And when molecules like benzalkonium or acetylpyridinium are introduced in the membrane of a bacteria or enveloped virus or protozoa, they destabilize the membrane, causing the bacterial cell to lyse. That makes sense. So cationic surfactants are more effective because they better stick, better interact, attach better to the negatively charged bacterial surface, and the mode of action is disruption of the membrane. Does that make sense? Can we move on? How effective they are. They are by no means sterilizing, they're disinfecting. So they actually have two modes of action. They can disinfect, and they also can help you mechanically remove the contaminant. Does that make sense? So for instance, when you wash your hands with a soap is more of a degerming agent, not antisepsis. When you wash your hands with soap, because it reduces the surface tension, it helps to lift microbial cells from your skin and just wash them away. Does that make sense? Good? Okay, we're going to talk about heavy metal, which I always like to talk about.